So in the past few classes, we have been talking about this particle size measurement, and in last couple of classes, we have discussed about this dynamic light scattering technique, which is one of the most well-known methods for particle size analysis. Now, there are a few more techniques which can be used to measure the particle size, and that is what we are going to discuss in this particular class. Okay, let us first talk about this technique. The technique goes by the name electrical zone sensing, and it is based on the change in electrical conductivity of a fluid in a small aperture due to presence of particles. And this change in the conductivity is proportional to particle volume in the aperture, and from there you can calculate the size of the particles. I'll come back to that in a moment, but before that let us have a look at the apparatus first. The apparatus which is used for this technique basically consists of a non-conductive tube with a small aperture dipped in an electrolyte containing the suspended particles. So here in this picture you can see the apparatus. Here is the tube that we are talking about, this one, which is dipped inside this electrolyte over here, and the aperture is over here, as you can see. So what is done is the fluid is made to flow in the aperture by a small pressure difference, which is created through a pump. This is the pump which is used for that. And in order to maintain the electrical current through the aperture, two electrodes are used. One is inside the tube and the other is outside. Okay, so this is what you see here. One electrode is here inside the tube and another is outside the tube. Okay, and through this the change in the current flow is recorded, and from there the change in the conductivity can be obtained, and that is finally used to calculate the size of the particles. And the dynamic ratio that can be obtained from this technique is around 30, and the lower limit of particle size that can be determined by this technique is 0.5 micrometer. So coming back to this, the change in the electrical conductivity and the way it varies depending on whether the particle is inside or outside the aperture, that can be seen from this particular diagram from here. So this is the aperture, the gap that you see over here, right? And this is the particle that we are talking about. So now you can see that when the particle is outside the aperture into the electrolyte, then there is a particular current which is flowing, right, which is here. That is the initial current. Now as you can see from here, as the particle enters the aperture, the current starts to drop, and you can see that drop over here. Okay, as long as the particle is inside the aperture, the current which is flowing is lower compared to the initial current, right? And the moment it goes out, the current again comes back to the initial value. Okay, so this drop in the conductivity that you have here when the particle is moving into the aperture, that is actually recorded in this technique and used to calculate the particle size. Because what happens is, here, as I said, the change in the current or the conductivity is actually proportional to the volume of the particles flowing into the aperture. So if you see the change in the current with respect to the size of the particles, the variation could be something like this. The first section is for large particles and the second one is for small particles. Right, as I said before, here also you can clearly see that the change in the current or the conductivity is proportional to the size or the volume of particles, and that is how the size can be calculated based upon the change in the conductivity. But of course, for that the instrument has to be properly calibrated before the measurements are done. And once that is done and you measure the current which is flowing, and from there measure the change in the conductivity, the particle size can be obtained. This technique is valid only when this relationship holds, wherein d is the particle size, rho m is the density of the metal or the particles, and rho f is the density of the fluid in which the particles are dispersed. And in this technique, particle settling is an issue, and that is particularly so for high density materials like iron and tungsten, which can settle down easily because of their higher density. And you also need to maintain a low concentration of particles to avoid coincidence in the aperture. Coincidence means multiple particles entering at the same time into the aperture. And the other problem is aperture plugging, which could happen due to the particles settling down into the aperture and not moving out. And also at times there are electrical noise. Okay, so these are some of the issues that you can encounter in this technique. And as I said, this technique is only valid for a particular relationship when it holds. Okay. The next technique that we are going to discuss is known as light blocking technique. This is similar to electrical zone sensing, but instead of conductivity, the decrease in light intensity as caused by the particles is recorded and correlated with the particle size in this case. The basic apparatus that you can see over here in this picture basically consists of a transparent tube in which particles are dispersed, as you could see over here, and then the particles are exposed to light beam. So here is a light source which is channeled towards the particles with the help of collimators. Collimators are essentially guide tubes which can channel the light in a particular direction. So as the particles come in front of the beam, they partially block the light and the intensity captured at the photocell detector decreases. Okay, so this is where the photocell detector is there to capture the intensity which is coming out after passing through this tube, right? So how much of the intensity will be decreased, and that will depend on the size of the particles. So assuming spherical shapes for these particles, the amount of light blockage is equated to an equivalent circular cross-sectional area, and from that the size of the particles can be calculated. Now, if you see the output from this photocell, it may appear something like this. The light intensity which is captured at the photocell detector, if you see it with respect to time, right? So the intensity can vary something like this depending on the size of the particles. And if you assume a spherical particle shape, from that, the extent of this intensity variation can be correlated with the size, and from that the particle size can be obtained. The dynamic ratio for this particular technique is about 45, and the lower limit of the particle size that can be determined depends on the optical resolution of the system, and it is typically around 1 micrometer. This is another method which can be used to determine particle size. This is based upon sedimentation, which is nothing but settling down of particles in a fluid. You might know that particles settling in a fluid reach a terminal velocity that depends on the particle size and the fluid velocity, and therefore the particle size can be estimated from the settling velocity. And here the Stokes law is used to derive the settling velocity, and from that the particle size is obtained. So the apparatus basically consists of a tube which contains a fluid in which the particles are dispersed, and when a particle moves through a fluid, these are the forces which will act on it. The frictional drag force Fv, which is given as 3 pi d v eta, wherein d is the diameter of the particle, v is the velocity, and eta is the viscosity of the fluid. So this is the Stokes law which gives this frictional drag force acting on the particles. And the other force which will provide a resistance to the movement of particles is the buoyancy, which is given by this, wherein rho f is the density of the fluid. And the gravitational force mg, which is essentially this one, will act downward. Okay. So when the terminal velocity is reached, the forces acting on the particle will be balanced. That means the forces acting upwards will balance the forces acting downward, which means that Fv and Fb the frictional drag force and the buoyancy will be balanced by the gravitational force Fg, right? And from this we can derive an expression for V. So let us write them in terms of their corresponding expressions. Fv is this, plus the buoyancy will equal the gravitational force. And from here you can derive V as so now if you can measure V, D can be easily obtained from this equation. So in order to measure V, there is an apparatus which is used, as I told before. That apparatus basically consists of a tube in which the particles are dispersed in a fluid, and a known settling distance is used, a settling height, let's say that is h, and in the measurement process the time taken for settling t is measured, and from here V can be easily calculated as h divided by t. Okay, so once this is obtained, it is replaced in this equation here and D is obtained. So if you substitute V over here, D will be obtained as square root of 18h eta by rho m minus rho f g t. Okay, so this is how you will get the particle size d from this sedimentation technique. But it has its own limitations. For example, it is limited to a narrow size range, and for particles below 1 micrometer there is slow settling and turbulence, and if there are internal porosity in the particle, that will reduce the mass and that in turn will lead to slow settling. And apart from that, the other difficulties that you can encounter in this technique is about the type of particles. For example, if you have irregular particles, the trajectory of the movement of particles through the fluid is not straight, and hence a constant velocity cannot be expected, and hence the accuracy of the measurement will not be good when the particles are irregular in shape. Okay, and also some prior knowledge about the particles in terms of their density and an approximate size is also needed beforehand to be able to carry out the measurement by this technique, and therefore it is difficult to apply for unknown powders where such properties are not known beforehand. Then we have this technique called air classification. This is nothing but a variation of the sedimentation technique. So here the powder is separated into selected size fractions using a cyclone or a spinning disc which rotates at high velocity up to 12,000 rpm, and a cross current airflow is used to separate out the particles as they fall on the rotating disc. Okay. So the centrifugal force due to the rotation of the disc will provide a constant particle velocity, and the airflow will result in separation by Stokes law effect. Now the way the particle size is distinguished here, or the way smaller particles are distinguished from the bigger ones, is because of the fact that the deceleration of the particles out of the disk depends on the size of the particle or the diameter of the particle and their mass. Okay, and therefore the lighter and smaller particles are deflected by the airflow and are separated from the larger ones. Okay, so that is how the size based separation happens in this case. The schematic of the apparatus is shown over here. It basically consists of this feeding hopper which feeds the powder particles onto this rotating disc, and as the powder particles fall on this rotating disc, they are given a velocity due to the centrifugal force as we discussed, and the cross current airflow, as you could see from here, will result in the separation of the particles based upon their size. And the rotational speed of the disc and the airflow velocity can be controlled to change the particle size separation, and that is how you can handle powders having a different particle size range. And the applicable size range for this particular technique varies from 1 to 150 micrometer. Okay, so before we finish this lecture, let us take a moment to summarize it. In this lecture, we learned about these 4 techniques of particle size measurement. These were elliptical zone sensing, which is based upon the conductivity change of a fluid as the particles move through a aperture in a tube which is dipped in that particular fluid in which the particles are dispersed. Then we talked about light blocking, which is similar to the elliptical zone sensing technique, but in this case, instead of the conductivity, the change in light intensity is captured, and from that the particle size is correlated to that intensity change, and the size of the particles is obtained. Then we discussed about sedimentation, which is based upon the settling velocity of particles in a fluid, and this is basically the Stokes law, which is applied here in order to get the settling velocity, and from that the particle size is obtained. And then we have also discussed a variation of this sedimentation method known as air classification, which uses a rotating disc and a cross current airflow to separate the particles based upon their size, and from that the particle size can also be obtained. So with that, we come to the end of this class. Thank you for watching.